Welcome to the Deep Dive, where we take the complexity of modern research and engineering, distill it, and deliver the insights you need to be immediately well-informed.
Today, we are taking a massive swing at the foundation of the current tech boom, generative AI.
Yeah, you really can't avoid it.
Not at all. Whether you've been stunned by the output of large language models like ChatGPT or, the photorealistic images from Stable Diffusion, these technologies have just dramatically changed the landscape in the last few years.
The headlines always focus on the stunning outputs, but our mission today for you, the learner, is to move past the demos and, frankly, the hype.
Right.
We want to give you a quick but genuinely thorough exposure to the core principles, the engineering breakthroughs that make these models actually work. The goal is to move you from just a user to an evaluator.
That's the key. If you boil it down, generative modeling is really just about teaching a computer program to create new data.
New data.
It consumes a huge data set, say millions of hours of speech, and it learns the underlying patterns and statistics so well that it can generate novel synthetic speech that sounds just like the training data, but it's never been heard before.
And the scope of what we can generate now is, it's truly staggering. Summarizing complex reports, generating code, synthesizing music, or creating these visual masterpieces we see everywhere.
Like that famous prompt.
A photograph of an astronaut riding a horse on the moon.
It's really the result of two parallel revolutions. The first is the transformer architecture, which gave us coherent, long-context language.
And the second?
The second is the diffusion model, which finally cracked realistic, controllable media generation. So let's unpack those two pillars.
Okay, let's start with language. We hear a lot about large language models, LMs, being predictive. But how predictive are we talking? Is it just glorified autocomplete?
Fundamentally, yes. But think of it as a highly optimized autocomplete. LMs work by predicting the next token a word, or even just part of a word, based on the preceding sequence.
So it's looking at what came before.
Exactly. The model calculates these likelihood scores, which are called logits, for every single possible token in its vocabulary.
So if I type, "It was a dark and stormy," the model is looking at all the potential follow-up words, night, day, Tuesday, and just assigns a score to each one based on its training.
Precisely. If night is token index 3729, and it has the highest logit score, then that's the most statistically likely continuation. Now, if the model always selects the single most likely token at every step, that's what we call greedy decoding.
And that sounds like it would lead to really boring, repetitive, or just locally optimal sentences that don't make sense in a broader context.
That's the trap.
You end up with a high score for the first few words, but the whole sequence just stalls out.
Exactly right. Let's visualize that failure point. Suppose your starting sequence is just the.
Okay.
Greedy decoding might say dog has a 50% chance, which is high. So you have the dog. Then barks has a 40% chance. So the total probability of that sequence, the dog barks, is 0.5 times 0.4, so 0.2.
That seems like a good, solid sentence. I don't see the problem yet.
It is, but there might be a better sequence hiding just beneath the surface, and that's where beam search comes in.
Okay.
Instead of committing to the most likely word immediately, beam search holds onto a fixed number of potential sequences, say the top 3 paths, and it explores them all simultaneously.
So it keeps a few hypotheses alive at the same time.
It does. Now imagine horse only had a 40% chance at the start. That's less likely than dog at step 1.
So Greedy would have thrown it away.
Immediately. But if the model explores that path and sees that runs follows horse with a 90% certainty, the sequence the horse runs now has a total probability of 0.4 times 0.9, which is 0.36.
Okay. I see it now. The total probability of the longer sentence is higher, even though the first word choice was less, locally optimal.
Exactly.
So beam search finds the globally more coherent and likely sequence. That's a crucial insight into why modern AI output sounds so much better than the early text generators.
It's a massive optimization in fluency. But let's talk cost, because that fluency definitely comes at a price. Training a model like GPT-4 required staggering amounts of data and compute.
We're talking millions of dollars, weeks of time, and huge carbon footprints. Most companies and individuals just can't afford that initial investment.
And that brings us to the immense value of transfer learning. You perform that massive, expensive pre-training once to create a base model with general intelligence.
Okay.
Then if you want that model to specialize, say, to generate documentation in your company's very specific, nuanced tone, you use fine-tuning.
And fine-tuning is the key because it's so much cheaper and more efficient.
Precisely. Fine-tuning an existing pre-trained model requires maybe 1% of the original data, takes hours instead of weeks, and you can often manage it on a single consumer-grade GPU. This democratization is what makes the technology so transformative.
And that pre-trained knowledge is so deep that it allows the model to perform tasks it was never explicitly trained for, like using it for classification, right?
That's zero-shot classification. You don't have to train a whole separate classification model. You can just prompt the generative model with, say, a movie review, and then ask it to assign a single token, positive or negative.
And it just knows.
It uses its vast pre-trained knowledge to predict which of those two tokens is the most semantically likely answer. It classifies a review without ever seeing a single labeled example during inference. It's incredibly efficient.
Speaking of efficiency and massive breakthroughs, let's pivot away from text and into the world of images.
Okay.
When diffusion models hit the scene around late 2020, they essentially replaced the previous state-of-the-art generative adversarial networks, or GANs. Why the sudden replacement?
Well, GANs were just incredibly unstable to train. They often suffered from what was called mode collapse.
Mode collapse.
Meaning they would stop generating a variety of images and get stuck generating only a few types, and often they were distorted. Diffusion models solve this instability problem completely.
And their method is actually pretty intuitive, which is what I love about it.
It is. Diffusion models are stochastic in nature, which just means they involve randomness.
So unless you set a specific seed, every time you run the same code, you're going to get a different novel image.
Exactly, and the core concept is iterative denoising.
The model learns how to undo a destructive process.
That's a perfect way to put it. During training, we teach the model how to progressively add noise, just pure static, to a clear image. Then we teach the model to reverse that process.
To look at a noisy image and figure out what to remove.
To successfully predict what the noise is, thereby removing it iteratively until a clear image appears. It's like sculpting something beautiful by chipping away at a block of marble.
And central to that sculpting process is something called the UNet architecture.
The UNet is critical. It was initially designed for highly specific tasks like medical image segmentation, where the output needs to be the exact same size and resolution as the input.
I see.
It's the perfect tool for this kind of progressive refinement because it maintains context across different scales as it strips away the noise.
So we have this theoretically brilliant model, but initially it required a supercomputer to run. What was the engineering insight that made models like Stable Diffusion possible for, well, literally anyone with a gaming PC?
That was the breakthrough of latent diffusion.
Yeah.
The problem was that applying that heavy noise and denoising process on full resolution pixels was just prohibitively expensive.
Too much VRAM, too much computation.
Every single pixel had to be handled. It was just too much.
So they needed a shortcut, a smaller canvas.
Exactly. Latent diffusion uses a component called a variational autoencoder, or VAE. Think of the VAE as a compressor. It takes the massive full-resolution image and compresses it into a much smaller, lower-dimensional representation.
The famous latent space.
The latent space.
So we are doing all the heavy sculpting and iterative denoising, not on the final enormous canvas, but on a kind of miniature, high-fidelity sketchpad.
That's a perfect analogy. The diffusion process happens only in that tiny latent space.
Yeah.
Once the denoising is complete, the decoder part of the VAE takes that clean, latent sketch and expands it back out into a full-resolution image.
And that single innovation just dramatically reduced the cost and time required.
Absolutely. It made image generation accessible and also highly useful for things like image-to-image transformations and editing.
That brings us perfectly to the next challenge. Whether it's a massive text transformer or an image diffusion model, they are enormous software artifacts. We now know how to train them somewhat efficiently.
Through transfer learning and latent diffusion, right?
But how do we run them on consumer hardware?
This is the practical hurdle. The sheer size of the parameters, the knowledge weights, often exceeds consumer memory. This requires aggressive efficiency techniques, and the main one is quantization.
I've heard that term. Isn't it just about reducing the precision? What does that actually mean in terms of performance versus quality?
It means we are sacrificing a tiny bit of numerical precision for a gigantic gain in memory savings. Model parameters are traditionally stored using 32-bit floating point numbers. Quantization techniques reduce that precision, often down to 8 bits, 4 bits, or even 2 bits per parameter.
So it's like we're taking the library of encyclopedias and printing them on microfilm. Same knowledge, just a far smaller footprint.
Exactly. You reduce the memory consumption by 75 to 90%, while only seeing a marginal, sometimes even imperceptible, drop in model quality.
Wow.
Now, for fine-tuning those massive models, we combine this idea with a technique called QLOR.
QLOR, it sounds like something you'd find in a really dense technical manual, but it's essential for democratization.
It is. QLOR stands for Quantized Low-Rank Adaptation. It's a form of parameter-efficient fine-tuning, or PEFT. The core idea is this. We freeze that enormous base model, that foundational knowledge, and we keep it quantized and memory efficient, let's say in 4 bits. Then we only add a few tiny trainable components called LoR adapters.
So the original giant library is frozen and stored compactly, and we only train and update a few, like, high-precision index cards.
That's the power. The small, adaptable LoRa adapters are kept in a higher precision, like 16 bits. This combination means you can fine-tune genuinely massive models, like the popular Mistral 7B, on GPUs with far less VRAM than the original training required.
It's what brings cutting-edge AI onto your desktop.
Absolutely.
This efficiency is amazing, but it still leaves us with a key utility problem. The models only know what they were trained on. How do we get these giant machines to reference knowledge that's real-time or external or proprietary?
That's the bridge built by semantic search and the RAID pipeline.
Rats.
Semantic search relies on a special type of transformer called sentence transformers. Unlike the LMs we discussed earlier, which output an embedding for every token, sense transformers are trained to output a single embedding that captures the semantic meaning of the entire piece of text.
Meaning I can take a complex user question, turn it into a semantic coordinate in a knowledge space, and find documents that are close to it in meaning, even if they use entirely different keywords.
Precisely. You are matching ideas, not keywords. That capability is the engine of the Retrieval Augmented Generation, or RAG, pipeline.
So how does RAG actually work in practice?
The pipeline structure is straightforward and highly effective. A user query comes in, step 1. A component called the retriever uses semantic search to look through an external knowledge base.
Your company's documents, regulatory filings, up-to-the-minute news.
Anything. And it extracts the most relevant snippets or context.
That retrieved context is then packaged up with the original query.
Exactly. Step 2. Both the query and that external context, say, the latest specifics of the European Union AI Act, which the model definitely wasn't trained on, are passed to the language model.
And the model gets new instructions.
It's instructed to answer the query only using the context provided. This allows the model to generate an informed, factually grounded response using external, verifiable data.
That solves the hallucination problem and the knowledge cutoff problem in one elegant architectural move.
It's the key to making LLMs reliable for enterprise use. Now, as powerful as these models are, we have to talk about the data they consume.
Right.
The sheer volume of scraped internet data is why they're so intelligent. But that data also imports significant and sometimes challenging characteristics.
You mean the models become mirrors of the vast, unfiltered internet they consume?
They absolutely reflect the patterns of their training data. We see this very clearly when testing prediction. For instance, if you ask a model to predict the profession for "this man works as a mask during summer,"
Okay, what does it say?
the predictions often skew toward physical labor roles like farmer, carpenter, or miner.
And if you just swap the gender marker.
When you input "this woman works as a mask during summer," the results often dramatically shift towards service roles like maid, nurse, or cook.
Wow.
And this isn't the model making a moral judgment. It is simply reflecting and statistically reproducing the gender stereotypes it observed billions of times in its training corpus. It's a direct consequence of data quality.
That reliance on massive, messy data also brings us to this thorny distinction between truly open source and open access in the machine learning world. They are not the same thing.
No, they are absolutely not. When we talk about a major company releasing a model, they are typically providing the model weights, the parameters, and the code to run it. This is generally defined as open access.
But true open source, in the software sense, requires the community to be able to audit and verify everything. So what crucial component is usually missing?
The full training data and the detailed training regime, they are almost never released.
And that's critical.
It's critical because without the hard data used to build the model, the public cannot truly audit its biases, its limitations, or even verify the safety claims made by the creators.
And the data itself is just a legal minefield.
It is. We are still navigating a massive legal gray area around copyright and fair use, particularly when datasets are scraped from every corner of the internet and then used commercially.
And safety.
Furthermore, safety auditing is incredibly difficult.
Sure.
For example, The massive LAION 5B dataset, a foundational source for many image models, had to be deactivated due to its failure to properly filter out explicitly illegal material.
So whether it's illegal gray areas, training data quality, or safety concerns, the access to this foundational data remains the primary challenge to fully understanding and governing these powerful tools.
That's the core tension. Society is trying to catch up to the technology, especially when accessibility is now so high. Accessible, real-time image editing, and the potential for deepfakes mean that the technical ability to create deception is now mainstream.
Even if some mitigation strategies exist.
Right, even if things like watermarking exist, the potential is out there.
So what does this all mean for the learner? We've covered a huge amount of ground today, from predicting the next word to compressing massive neural networks.
Our journey today really highlighted some critical engineering trade-offs. We saw the trade-off between speed and coherence when comparing greedy decoding to beam search. We analyzed the trade-off between pixel perfection and massive efficiency gains when moving from pixel-based GANs to these latent space diffusion models. And we looked at the engineering solutions, quantization and QLoRa, that solve the memory and training constraints.
We've established that specialized architectures still reign supreme for certain tasks. You've got encoder-based models for fast classification and retrieval, and then generative models for creation. This prompts a final question for you to consider.
As generalist models continue to grow in size and capability solving tasks like classification, summarization, and generation in a single zero-shot swoop wheel specialized, smaller models still maintain a decisive edge in applications where speed, efficiency, and, mandated guardrails are paramount.
Or is the future destined to be dominated by one colossal general-purpose model?
That's the question driving billions in R&D today. And the sources we reviewed provide an excellent launchpad for your own exploration into the future of this field.